So, what can you tell me about the coordinates of this red point right here? What was the big point that we made at the end of class last time about this point and its coordinates?
You plug into the equation and it equals 7.
Okay, so Kaylin said if this is the x coordinate and this is the y coordinate, you're saying you want to plug it into this?
Yes.
And what will happen?
It will equal 7.
It equals 7. So I'll do it, right? So I'm going to take a squared plus b cubed minus 2ab. And it'll tell me right there. So it's giving me the value of the expression when a and b are these values. And that's this point. And so we're basically saying when you look at that pink curvy curve, what does it represent? What does that pink curve represent? This was the big point for Monday. What does that pink curve represent? Yeah, Sean.
All the values where the equation.
Okay. Right. Yep. Now all the what? So this curve is all the.
All of the values x and y.
Okay. So the curve is all the points, right? The points whose coordinates x and y do what? Make this.
Make that equation equal.
That's right. And what about this? So now what about here? 1.35 and 2.7. What does not equal 7?
Equation with x squared plus y equals 2x.
Right. If you took the coordinates of that point and put them into that expression, what will happen? You won't get 7. What will you get? 14.8582, which does not equal 7. Therefore, it's not one of the points. That is, so we're associating this equation right here with that pink curve. It's a mathematical association, not just this equation is the label or the name of that curve, right? That curve is a representation mathematically of this equation. Okay, and so then we talked about rate of change. So because it's a curve, as we move along this at any given place, y has some relative change. Some is changing relative to x at any given place. Would you agree with that? And so we can talk about rate of change. So what's the rate of change of this curve when x equals 3? What's the rate of change of this curve when x equals 3?
A couple of different points.
What's that?
There's a couple of different points.
He says there's a couple of different points. A couple is 2. Is that right?
There's 3.
There's 3 actually, right? So x equals 3 somewhere around here. X also equals 3 here. And likewise here. So on a curve like this, when I ask you what's the rate of change, what do I need to specify?
At which y value?
Yeah, so not only do I have to say what's the rate of change at x equals 3, but then I have to say what's the rate of change at x at, say, x equals 3 and y equals something, right? So I need to not only specify x, but also specify y. How well I'm going to do here. There we go. So this is the point. We'll just round. So 3 and 2.26. Now that I've given you x and y, we can talk about the rate of change there. So, talk to me about the rate of change there. What do you think? So if we wanted to talk about the rate of change at this point 3, 2.26, what would we do, or what would we talk about? What's that? Yes. Thanks. What would that conversation be like if we were just to say, what's the rate of change here at 3, 2.26? Christian?
Would you maybe try finding the derivative of the label or of the x squared plus y cubed minus 2yx?
Okay, great. So we're learning that derivatives give us this new function that will give us rate of change. Okay, so that would be one route. Would be from this equation. Could we get a derivative function or derivative equation that could give us the rate of change? But what if we? What about more of a visual route, Nicholas?
Could you just use the x and y coordinates as your delta x and delta y, and then use that to figure out the k?
Okay, so you want to take 2.26 divided by 3?
Yeah.
What about 2.26 divided by 3 to get a rate of change? Does it work? Peter?
You need 2 different points. You need like a slight change off of 3, 2.26, and then subtract those values and then divide the delta x divided by delta y.
He wants delta x, so this would be x and y. So rather than divide y by x, he's talking about dividing delta y by delta x. Better?
Yeah.
Yeah. You can, so yeah, we need a change. Okay. So we need a slight change. And so what can I do to? What can we do? So we want to estimate the rate of change here, just visually. And so we know that that is delta y. Delta x is our k. How are we going to do that? So like, what about this? Here's a delta x and the corresponding delta y. How about that? So I got a delta x, I got a delta y. I can get the rate of change. What do you think about that, Shayna?
Don't you have to like zoom in so you can get local linearity?
She said we want to zoom in so we can get local linearity. Kirsten likes it. Marco, what do you think? How about what I picked? Delta x and corresponding delta y. Not sure. Austin?
It's just giving the average rate of change from 3 to 4.
Okay, nice. Okay, so he's saying if we do that, delta x over delta y, it would be like an average rate from 3 to 4. And would that be an accurate estimation of the rate at 3?
No.
No. And so what do you think about Shayna's suggestion?
I would go with that, yeah.
Yeah, so what we want to do is there we go. Okay, so I'm gonna if you put this on graph calculator, put the crosshairs on the graph and then zoom in, it'll keep that at the center. So 3 and 2.26. Okay, so now we'll just take another point, and we probably need some more decimal places here. So let's do 3.003. Say 3, 4, comma, 2.2613. Okay, and then what can I do? So we're going to invoke a little change in x. If I can make numbers nice. Oh, there was a nice, there we go. Here is 3.01 and 2.2602. So there's 2 points on the graph. So estimate the rate of change. Estimate the rate of change. Go. So estimate the rate of change based on these 2 points.
No.
Sure, that doesn't let me do it anymore. Okay, so there's these 2 points that we got on the curve. I got the coordinates. So tell me, did you find the rate of change? Janae?
Negative 0.6.
So tell me your process.
So I took negative change in y over
Okay?
subtracted 2.2613 from 2.2602.
I think you mean the other way around, right? 2.2613. Oh, no, you're right. No, you're right. You took you subtracted 2.2613 from that's right, 2602. Oh, before we do this, we should have estimated. Sorry. We should have tried to estimate it. So what would you now we're staring at the value. So what I intended to do was before we found that value to actually estimate what we're looking at. But I guess that's too late now. 2.2613 divided by okay. Negative 0.17. Is that about right? Is that what you got? Okay. So I want you to just have a short conversation. What does that number mean? Does it make sense given the situation? So what does it mean, and how can we make sense of it given what we're looking at? Go.
The change that's really small. Yeah, single change. So we just change the first phrase. Yes. That's what we're trying to find. Change.
Okay. Let's regroup. All right, so this, I've said this before, but this conversation right here is arguably the most important conversation we have all semester, okay? And we've done it over and over and over again because this is the essence of rate of change. So, Zoe, how'd you do? Can you tell me what is the meaning of this number and how can we make sense of it in this situation?
When x is equal to 3 and y is 2.26,
Okay.
basically around that, then the rate of change at those points is negative 0.17.
Okay, so that's stating that when x equals close to 3, the rate of change is negative 0.17. And so what does that mean? What does that number mean?
That the y value is changing negative 0.17 times as fast as the x is changing.
The y value is changing negative 0.17 times as fast as the x value. Agree with that? All right, let's hear a different interpretation. So yeah, absolutely right. Okay, and so how can we make sense of that y is changing that times many as fast as x? Chloe?
Every time that x changes a small amount,
Okay.
it will change by x times negative 0.17 times that amount.
Every time x changes a small amount, how much does y change? and about negative 0.17 times the change in x. And we got to say about because this is really isn't constant, right? If we can zoom in close enough, it's very, very close to constant, but that rate is changing continually, right? So, and she said for a small change in x, right? For a small change in x, the change in y will be about negative 0.17 times the change in x. Okay, who can make sense of what we're seeing there? So this is really crucial. So those are both correct in terms of making sense of that number. But how can we make sense of what we're seeing relative to that y is changing that many times as fast as x? So how can you bring the visual into it? Ryan.
Horizontal line.
Okay. From here?
Yeah.
My pen's a little too thick, so maybe we'll extend it out further. Okay, we'll go out this far. Okay.
And then you need to draw a vertical line from that.
And what is this representing?
That's changes in x.
That's a change in x. Okay. And then you want a vertical line.
To represent the changes in y,
Okay.
which is equal to negative 0.17.
Darn it. Let's try again.
Approximately.
So we can make kind of a triangle. I had to make it bigger. I wanted to make it there, but it's fine. We can make it a little bigger. And so how does this triangle show this value? How does that triangle show this value? I know Christian knows. Kevin, what do you think? What's that?
Yes, question.
How is this triangle revealing the meaning of this value right here?
Well, the chart, that's always going down. So
Going down?
instead of negative,
Good. Okay, so it's the y's are decreasing, so our rate is negative. Good.
and that is going towards the right, which makes that positive, which makes it negative in total. The delta y is a smaller change than delta x.
Okay.
So that's why it's a 0.17, not a 1 point something.
Nice. Okay.
So it's not like 1 times the total. But also, it's deflecting right now.
All right. Excellent. Yeah, Jamal.
Is the hypotenuse of that triangle?
The hypotenuse, in terms of the length of it.
Yeah.
What about it?
Would have been if we went to the original point.
Okay. All right. So how can we make sense of this? How does this picture make sense of negative 0.17, or how can we draw those two together? Yeah, Nicholas.
The delta x, the length of the delta x, is negative 0.17 times as long, or as long as the delta y.
Length of delta x is negative 0.17 times as long as this one. Is that right?
Or did I say that backwards? Other way around.
Other way around.
Yeah.
Okay. So the length of that delta y is, or the change, that change
Negative 0.17 x.
is negative 0.17 of that. So whenever x changes near 3, what can you say about how y changes? Whenever x changes a little bit, increases a little bit, how is y changing?
It's almost the same.
It's changing the same amount. A little bit, that's changing a little bit less than x.
Right.
Think of it in terms of percent. How much is y changing relative to how much x changes? What's that? 17% of yeah, so whatever x change we make near 3, y is going to go down about 17% of that change in x. Okay, so we have a gradual decrease. It's a gradual decrease because it's less than 1/5, right? So it's going down less than 1/5 the amount that for whatever change in x we had, or about 17%. And so we see this gradual decrease in y as x increases, right? Gradual decrease. So around 1/5 or that's actually 1/6 exactly, right? Negative 0.16667.
Yes.
Yeah, so y is always changing, or not, in the vicinity of 3, y goes down 1/6 as much as x increases. for small changes in x, or a gradual decrease in y. Okay, so then Christian had this suggestion that we should come up with a rate of change equation. Okay, and we can do that. But what's the obstacle for that? So here we have this equation, x squared. What's that? Well, we had x and y before, so all these ones you were doing for the getting ready for the mastery exam all have x and y in it. So what's different about this? What's that? Solve for y. Okay, so if we were to solve for y, we could try to get some, say, call it e of x, some equation of x, or expression of x, some expression of x. Can we do it?
Yes.
Not easily. And we could make that a lot more complicated and intertwine x and y together more tightly, so that it'd be hard, very difficult to do this. Okay? So how we approach this is we pretend that this exists, but we don't find it. Okay? So we pretend this exists. There's some expression of x that if we plugged our x in, it would give us the corresponding y for this equation. So pretend this exists. But we never find it. Okay? So then what we do is we can still apply all the same rules that we did before. So I'm going to take the rate of change of the left side. And so if those accumulations are equal, that amount of accumulation is equal, then the rates of change is going to be equal. Is that fair? Yeah, so if those two things are equal, then the rate of change of that with respect to x is going to equal the rate of change of that with respect to x. And so now we've got the sum and difference rule, and so we can do these one at a time. We can do these one at a time, but we have to remember that when we get to y, we're integrating with respect to x, or sorry, taking the derivative with respect to x, y is some equation of x. So we have to remember that. So let's start here. So what's the rate of change of x squared? 2x. Okay, and so now we have to think of this y cubed. Y is an equation of x, so this is an equation of x cubed. We just don't know what that equation is. So how do we handle that derivative? So what is the rate of change of that with respect to x? 3. Okay, and so let's see. Equation of x squared. Are we done? No, it's chain rule because, right, this is some expression of x. We don't know what it is, but we know that it exists.
So y prime?
Times
I'm sorry, I should use prime.
the rate of change of
Change of y.
y with respect to x. So we have to use chain rule on that. This is our expression of x, and this is that expression, the rate of change of it with respect to x. Okay? What about minus 2xy? Negative 2 y prime.
Y, yeah, rate of change of y.
So what do we have? We have 2x times an equation of x. How do we take the rate of change of that? You need the product rule. So hopefully if you weren't thinking product rule and you were concentrating and looking at that and weren't thinking product rule, you just got caught. Okay, you got to be able to see that we're multiplying two functions of x together. That's product rule. Okay, actually minus. All right, so we'll take the first times the derivative of the second, which is y prime, right? Plus the rate of change of the first times the second. Did you catch it? So those two terms are the product rule on that right there. Rate of change of 7 with respect to x. 0. Okay, so we're making progress here. Any questions on what I just did right there? Yeah.
Why do you multiply 3y squared times the rate of change of y?
Because what is y? Y is an equation of x. I'm looking at this right here. How would you take the rate of change of that? You would need the 3 times that thing squared, but then times?
The product rule?
Not the product rule. This is the chain rule, right?
Uh,
This is a composite function. It's an equation of x plugged into something cubed. So the structure of it is something cubed. So we do 3 times that thing squared. But then by the chain rule, you have to multiply by the rate of change of what's inside. Remember that? You should be doing it lots for practice, right? So that's what that is right there. Yeah. What is the rate of change of 7 with respect to x? What is 7 with respect to x? Take the derivative. What's the derivative of 7? That's what I'm doing. Make sense? It's a constant, right? Whenever you have a 7, whenever you have a constant, derivative is 0. Ross?
If we're using y as a function of x,
Yep.
why can't you write it like that? Why do you have to use y?
Because this is difficult to solve to get it. Because I have a 2xy and then a y cubed. It's very difficult to get y as an expression of x. And we could make it a lot worse. And we'll see another example where you could have y embedded in cosine and then as the exponent of e and then...
No, but I mean like in the derivative, why can't you, instead of writing y, you write e of x?
I could. Yeah. So exactly. So I could have done this. I just was kind of taking a shortcut. Is this what you mean?
Yes.
Yes, this is totally valid.
That's where that y prime comes in handy.
That's the exact same thing. So maybe the first time I should have wrote that. Okay, it's this first time I should have wrote that out. But that's what we're doing. But it's just so we just remember that y is an expression of x, and so from here on out, whenever we have y, we can just write it as y. And whenever we have the chain rule for that rate of change of the inside, we can use y prime. Okay, what from here? So what are we after? We're after what? The rate of change of y with respect to x. So what in this are we focused on to solve for? Y prime. Okay, so here's what we do. Everything that has every term, so we have 4 terms here, 1, 2, 3, 4. Every term that has a y prime, we're going to leave those on the left. Every term that doesn't have a y prime, we're going to move it to the right. And that way we're moving towards isolating this y prime. So in the end, we can get y prime equals something. Okay? So we're going to keep everything with y prime on the left. 3y squared, y prime, minus 2x, y prime, equals. So we're going to move this one. Doesn't have a y prime, so it's going to head over here. Minus 2x. Similarly, the minus 2y, move it to the left, to the right. So we're one step away. So what's the next, one more step? What do we want to do to isolate y prime here? Factor it out, right? Last step, divide by that. So this is just a lot of algebra, moving things around. That first step is maybe the most important. Okay, did I lose you? Let's look at this. So this first step is taking the derivative of both sides, getting the rate of change of the left and the rate of change of the right side, and they'll be equal. From there, we need to get all the terms, we have 4 terms, all the terms that have a y prime to the left side, everything that doesn't to the right, so that we can factor out that y prime and isolate it and solve, get the expression that it's equal to. Any questions?
So we plug that back into the top one?
So what now?
So we plug that back in now? Like now we know what it is?
No, so now let's explain. What is this equation? What is this about? What does it help us do?
That's derivative.
It'll give us the rate of change of how y changes with respect to x on this in this equation. But look, what do we need now? So when you look at this equation, this is what we talked about earlier. You not only need x, but you need y too. See, you need, so this matches up with what we said before. If I just said, what's the rate of change at x equals 3, it's not enough. You need the y value as well. So what was the point? We had 3 point, what was our original point? 3 point,
2.26 or something.
wasn't it 3.0?
Yeah.
0034 and
2.2613.
so what I want you to do, so what we're going to do is let's find the value of the rate of change now using the equation. So we're going to take the x and that y and put them in, and we can do it right here on graphing calculator. So I have it right here. And looks like I did this last semester. 3.0034 and 2.2613. So I set up the rate of change function here that we just found, negative 2x plus 2y, or 3y squared minus 2x. And then I plugged in that point that we looked at, 3.0034, 2.2613. Okay, so this was everything was estimations, right? But look what we got, negative 0.16. Okay. So why isn't it exactly what we had before? Because everything we're rounding, right? We're rounding all these values that we're picking off the graph and when we make calculations. So about the change in y is about negative 1/6 of the change in x. Okay, does it make sense? So let's look at those other points at 3. So can I erase what's on the board? What I wrote? Can I take it off? So let's go back. Let's reset the graph. So now I want you to estimate. Don't do anything yet. Here's another point at 3. So here's 3 and 0.35. 0.34. So here's another point. So have a conversation. First, estimate the rate of change visually, and then use the equation or talk about what that means. So estimate the rate of change visually, talk about what that number means, why it makes sense, and then use the rate of change equation to confirm your estimate. Okay, go. So it's 3 and 0.34.
Yeah.
I see it again.
Oh, just kidding, sorry. Okay.
Okay, Connor, what do you think about an estimate for this rate of change at 3, 0.34? Just by looking.
Maybe a positive.
He said positive 1. Molly, agree with that?
Yeah.
Is that ball? It's an estimate, so ballpark.
Yeah, so yeah.
Okay, so yeah, so it's not 2, it's not 10, right? But it might be, it might be 0.8, 1.2, something around 1. If you said something close to 1, that's a pretty good estimate. Okay, so now let's check it. So what are we saying? That changes in y around 3, 0.34 or what? What can we say about it? Yeah.
Or about the same as change in y.
About the same as
Change in y.
the changes in y come from changes in x. So the change in y is
Same as change in x.
about the same as the change in x. So if we make if x changes a little bit around this point, 3, 0.34, we expect y to change about the same amount, increase the same amount as x. And that's what a rate of change of 1 is. Okay? So let's check it. 3 and 0.34. 0.94. Okay? So the rate, according to the equation, 0.94 is the rate of change. So 1 is a good estimate. Make sense? What's going on? Yeah.
So this equation that we like derive, it,
This one?
like, yeah, is that like the exact rate of change for that
Right.
curve?
It's like all these closed form rates that you're finding for your.
Okay, and then we just found it by using I got it.
We'll do another one. We're going to do another one. Okay. So here's a slightly harder one. And it's good practice for some of our rules. And it makes a cool graph. All right. So let's do this one. So let's look at the graph first. Okay, but what does it mean? So what are you looking at when you look at those blue curves? What are you looking at? Can you explain it, Aaron? So when you look at those blue curves, what are you looking at?
All the points that correspond to that function.
Okay, all the points whose what? Whose coordinates x and y
Make that equation.
make that equation true. Make that equation true. If you're looking at every point whose x and y coordinates make that equation true. Okay, so let's find the rate of change function. Here we go. So we're going to take the rate of change with respect to x over here, and the rate of change with respect to x over here, and we are pretending, right? We're pretending that we're imagining that y could be considered some expression of x. Okay, so rate of change with respect to x. Who's ready for tomorrow? This counter over here. Negative sign of y squared times 2y. Okay, ready for the next one? But what is y? Y is some expression of x, and we're taking the derivative with respect to x. So are we done? Nope, we need. Do you see that? You got to see that. That we're imagining that y is some expression of x. If we were able to rearrange this and get y as an expression of x, which we can't, okay, here's one where it's just like impossible. We have to imagine that, and so every time we're differentiating with y, there's always going to be a chain rule because that y is an expression of x. Okay, next part. Who wants to help me with this? How are we going to approach x square root of y? Product rule. Okay, so plus the first times
1 over y times y prime.
Okay? What is square root of y? 1 over.
2. Oh, 2.
Can I do it this way? Y to the? Avoid fractions here because we're going to be moving things around. Okay, so that's the first times the derivative of the second. We done? Times y prime. We just differentiated a y. And every time we differentiate a y, we're going to have to tack on by the chain rule the rate of change of whatever that expression is. So we'll call that y prime. All right, plus. So what do we do? We did the first times the derivative of the second plus derivative of the first. That's easier, right? Okay. Derivative of minus 2, 0, equals? What's the next step? So we're going to, everything that has a y prime on the left, everything that doesn't have a y prime on the right. Okay, so since those are both right here, can I also factor in one step here? Can I skip a step? So I'm going to go ahead and factor this right here, because these are the two that are going to stay, right? These are going to stay. This is going to move over. So I'm just going to factor out that y prime right now, for time and simplicity's sake. Plus 1/2 x y to the negative 1/2. Equals x to the minus 1 minus y to the 1/2. Okay, rather than write out the next step, I'm just going to type it in graphing calculator. Is that fair? So now the next is going to be our rate function. Okay, what will it be? So we're isolating that. Okay, so this will be the numerator, right?
And what's in parentheses would be denominator.
That's right. I'll just change this back to square root of y now. It's okay. Y to the 1/2. Divided by this unfortunate line on the screen. Sorry about that. All right, so negative sine of y squared times 2y plus 0.5 x y to the negative 0.5. Can I erase what I've wrote? Everyone got it?
Is it on the numerator, is it necessary to take it back into the square root, or can you,
Nope.
you can keep it as a half?
Keep it a half. Same thing. That's what that means. Square root means to the 1/2.
I just want.
Yep. Square root means to the 1/2. Okay, so there is our rate of change function for that right there. Okay, so what's the rate of change at x equals 1.5? What's the rate of change at x equals 1.5? How would you respond to that question?
You know why that?
Which y? Okay, so let's go with this first one right here. So estimate it. 1.5, 2.21 is the point. 1.5, 2.21. Estimate the rate of change there. What do you think? Gilbert, if you were to estimate the rate of change right there. What would you say?
Thinking -1/3.
Negative 1/3. What do you think of that estimate? Jonathan likes it. Okay. So how can we check? Piece of cake, right? Graphing calculator makes this very easy. We just do the rate at 1.5, 2.21. Okay, so he said negative 0.33, it was negative 0.17. That was, yeah, that's a decent estimate. Yeah, question?
Is it possible to graph the rate of change function, or a rate of change, or is that not going
Okay.
to work since the input's x? And
So is the rate of change a function? Given a value of x, do you get one rate of change? So we can't graph it. We might be able to graph it in three dimensions, but we can't graph it here because, well, this isn't a function. Let's give it a shot. See what happens. This might be scary, but we're okay. No, so I can't do that because no, I can't do it because the rate is a function of x and y.
yeah, so
Yeah, I can't do it. So yeah, we'd have to graph it in. If I do this, we're gonna get a three-dimensional graph. I'll make it gold. Ready? Here we go. Oh, it worked.
You've got y equals r.
What's that?
You've got y equals
Oh.
r.
Right. Well, so now does that work then?
Can you change the color of it?
Yeah. No, this works. So look. So at x equals 3. So at x equals 1.5, we have all these different places, right? With different rates. Okay. I think what this is showing us right here is this rate that we just found, negative 0.168. That might be that value right there. No, it's not, because it'd be negative. That doesn't work. Okay, it doesn't work. So we do z.
That looks so cool.
Yeah, but do you know what you're looking at? Do you understand what you're looking at?
Level 3 inspired.
Okay, so of course your mastery exam is tomorrow, and don't forget homework for Friday. There's homework for Friday. Both. It's two. You're handing in paperwork in class and my math lab both.